On September 24, 2023, a capsule the size of a mini fridge slammed into the Utah desert at 27,000 miles per hour. Inside it were 8.8 ounces of black dust and rock fragments, collected from an asteroid named Bennu. Scientists celebrated. The media covered it as a triumph of space exploration. But what they didn't say in the press conferences was this: the data from those samples had just changed the math, and the new numbers were worse. Bennu is currently 200 million miles away, orbiting the Sun in a path that crosses Earth's orbit every 6 years. It's roughly the size of the Empire State Building, 1,610 feet across. If it hit Earth, it wouldn't cause a global extinction, but it would release the energy equivalent to 1,200 megatons of TNT. For context, the largest nuclear weapon ever detonated was 50 megatons. Bennu would hit with 24 times that force. The impact zone would be vaporized. Cities within hundreds of miles would collapse from the shockwave. Dust would choke the atmosphere for years, and the moment scientists recalculated its trajectory using data from those 8.8 ounces of dust, the probability of impact in 2182 increased, not by much, but enough to matter. Bennu was discovered in 1999 by the Lincoln Near-Earth Asteroid Research Project in New Mexico. At first, it was just another entry in a growing catalog of near-Earth objects, asteroids whose orbits bring them uncomfortably close to our planet. But as astronomers tracked it year after year, they realized something unsettling: Bennu's orbit wasn't stable. Every time it passed near Earth, our planet's gravity tugged on it slightly, altering its path. These perturbations are small, but they compound, and over decades, they make prediction nearly impossible. By 2016, scientists had calculated that Bennu had a 1 in 2,700 chance of impacting Earth on September 24, 2182. That's a 0.037% probability. Statistically negligible, right? Except asteroids don't care about statistics, and 157 years is not as far away as it sounds. People born today will have grandchildren alive in 2182. The question wasn't whether Bennu could hit us. The question was, how do we change those odds? NASA launched the OSIRIS-REx mission in 2016 with 2 goals. First, collect a sample from Bennu's surface and bring it back to Earth. Second, measure the asteroid's mass, composition, rotation, and orbit with unprecedented precision. Because here's the problem: you can't deflect an asteroid if you don't know exactly how it moves. And Bennu was full of surprises. When OSIRIS-REx arrived at Bennu in December 2018, mission scientists expected a relatively smooth, sandy surface. What they found instead was a chaotic landscape of boulders. Some were the size of cars, others the size of houses. The largest boulder on Bennu is 460 feet across and sits near the equator. The team had to completely redesign the sample collection strategy because the planned landing site chosen from telescope images taken from Earth turned out to be covered in rocks that could have damaged the spacecraft. But the biggest shock wasn't visual, it was thermal. Bennu is what's called a rubble pile asteroid, a loose collection of rocks and dust held together by weak gravity. It's not a solid object, it's more like a flying gravel heap. And when the sun heats one side of Bennu, the rocks release that heat unevenly as the asteroid rotates. This creates tiny thrust forces called the Yarkovsky effect. Over time, these microscopic pushes alter Bennu's orbit, and they're almost impossible to predict without direct measurement. The Yarkovsky effect was first theorized in the early 1900s, but it had never been precisely measured on an asteroid until OSIRIS-REx. The spacecraft spent 2 years orbiting Bennu, tracking every wobble, every rotation, every subtle acceleration. What the data revealed was this: Bennu is drifting off course faster than models predicted, not by much, but enough to shift the probability calculations. Here's where it gets uncomfortable. Before OSIRIS-REx, the predicted impact probability for 2182 was 1 in 2700. After analyzing the spacecraft's orbital data and the physical samples returned to Earth, scientists recalculated. The new probability is approximately 1 in 1750. That's a 54% increase. Again, it's still a small number, but the trend is what matters. The more we learn about Bennu, the less certain we become, and uncertainty in this context is not comforting. The composition of the returned samples added another layer of complexity. The dust and rock fragments from Bennu contain high levels of carbon, water-bearing minerals, and organic compounds. That makes Bennu scientifically valuable. It's essentially a 4.5 billion-year-old time capsule from the early solar system, but it also makes it unpredictable. The water content affects how the asteroid responds to solar radiation. The carbon changes its reflectivity, which changes how much heat it absorbs and re-emits. Every detail matters because every detail affects the math, and the math determines whether humanity needs to act. There are currently about 34,000 known near-Earth asteroids. Of those, roughly 2,300 are classified as potentially hazardous. Asteroids meaning they're larger than 460 feet across and their orbits come within 4.6 million miles of Earth. Bennu is one of them. But here's the terrifying part. We've only found an estimated 95% of asteroids larger than half a mile across. For objects Bennu's size and smaller, we've found maybe 50%. The other half are out there, invisible, untracked, and some of them are on collision courses we don't know about yet. Bennu is not the most dangerous asteroid we know of. It's just the most thoroughly studied. We know its size, its shape, its mass, its composition, its rotation rate, and its orbit down to the meter. We've touched it. We've brought pieces of it home. And even with all that knowledge, we still can't say with certainty whether it will hit us in 2182. September 24th, 2182 is a Saturday. Bennu will pass within 750,000 miles of Earth, about 3 times the distance to the Moon, close enough that Earth's gravity will significantly alter its trajectory. What happens next depends on thousands of variables we're still measuring. If Bennu passes through a specific region of space, scientists call it a gravitational keyhole. Earth's gravity will bend its orbit just enough to send it on a collision course for a future pass. The keyhole is only a few hundred meters wide, but if Bennu passes through it, the next encounter could be catastrophic. We won't know which path it takes until it's too late to do anything about it in that moment. The deflection, if needed, would have to happen decades earlier. NASA has already tested asteroid deflection technology. In September 2022, the Double Asteroid Redirection Test DART mission intentionally crashed a spacecraft into Dimorphos, a small moon orbiting the asteroid Didymos. The impact changed Dimorphos's orbit by 33 minutes. Proof that kinetic impactors work. If we had enough warning, we could do the same to Bennu, but enough warning means decades, not years. And enough funding means billions of dollars for a threat that might not even materialize. That's the political problem. It's hard to justify spending billions on something that has a 99.9% chance of not happening. But if it does happen, the cost of doing nothing is incomprehensible. A Bennu-scale impact would not end civilization, but it would destabilize it. Depending on where it hit ocean, city, farmland, it could kill millions, disrupt global food supplies, trigger economic collapse, and create refugee crises that would dwarf anything in human history. And Bennu is just one asteroid. There are thousands more we're tracking, tens of thousands we haven't found yet, and some of them are much, much larger. Right now, Bennu is a distant speck of rock tumbling silently through space. heated on one side by the sun, cooling on the other, drifting ever so slightly. Of course, because of forces we only recently learned to measure. In 2182, it will pass close enough to Earth that people could theoretically see it with binoculars. A dark point moving slowly against the stars. Whether it stays in the sky or becomes a flash of light brighter than the sun depends on calculations we're still refining and decisions we haven't made yet. The samples sit in a lab in Houston. The data is being analyzed. The models are being updated, and the countdown continues. We know when Bennu will arrive. We know how big it is. We know what it's made of. What we don't know yet is whether 157 years is enough time to be ready, or whether we'll even try. Because the most dangerous thing about Bennu isn't the asteroid itself. It's the gap between knowing something could happen and actually doing something about it. And in that gap, the clock is ticking.